Hi everyone. So today we're going to look at the Laplace form of circuits, and essentially what this means is that we're going to convert the circuits directly into the Laplace domain without going into the differential equations. To do this, however, we do have to look at the differential equations, but once we derive the equivalent Laplace forms, just like we did when we use the tables, we no longer have to go back to the integrals and differentials and so on. So we start off with the VI characteristics of each device, the resistor, the inductor, and the capacitor. And essentially what we're going to do is we're going to map IT to IS, and VT is going to map to VS. So for the resistor, we could see that V becomes capital V. So VT goes to VS, IT goes to IS. For the inductor and the capacitor, we have the derivatives. So we have to look at what our the corresponding property to transform or to manipulate our Laplace equivalent of IS to SIS minus I0, and the same thing for V. This should actually be, since we're changing VT here, this should be VS and V0. Now, one important thing to note is that the I0 here and the V0 here, these are not in the S domain. These are actually your initial conditions that you get in the time domain. They are constants. They are not functions of time. They are constants which represent the initial conditions on the circuit. So if we transform the resistor to the S domain, we will see from our equation we went from the time domain here to the S domain here, and we have basically the same relationship. So V is equal to IR. This is our impedance term, so it goes in the circuit, and we have VT going to VS, IT going to IS, and the only thing that is relating them is the impedance term. So we draw it the same way in the circuit. When we move to the capacitor, it's a little bit different. We now have a differential, a derivative. So when I write this either in derivative form or in integral form, I can bring those into the S domain as we showed previously, and then I could see that, for instance, here IS is related to VS through this admittance. Remember, V is equal to IZ, where Z is the impedance, or I is equal to Y V, where Y is the admittance, which is simply 1 over the impedance. But since we're plotting impedances, since we're drawing impedances, this means that 1 over SC will be the impedance. And this CV0 now, since we're looking at current, is a current source. And since it is negative, it will be going in the opposite direction to IS. Now we could also represent this, and you'll see here this is essentially a Norton form. We could also represent it as a Thevenin form. So we have IS on SC plus VC0 on S, which I get if I rearrange the equation, or I could do it this way from the integral. And in this case, 1 on SC, V is equal to IZ. 1 on SC is the impedance Z, which is the same from this side. And then VC0 on S is the voltage source, because we're looking at voltage now. So you see here we get a Thevenin equivalent, and you could see you could convert these back and forth, Thevenin to Norton, and you should get the same thing. So if we move on to the inductors, again we do the same thing. We write our differential or integral equation, we convert it to the Laplace domain, and we will see here V is equal to something multiplied by I, which would be the impedance, plus Li0. So in this case, our impedance is SL, and we have a voltage source which is negative here. which means it goes in the opposite direction to Vs. It goes in the opposite direction to Vs. Or we could do it as a current source by rearranging the equations or by using the integral form. And just like we did previously with the capacitor, we could also use a Thevenin to Norton transformation, and we will get the Norton form of the circuit. So essentially what we're going to do when we map a circuit in the time domain to a circuit in the S domain is we're going to look at the inductor here and we're going to replace it with either this circuit or this circuit. And this will take care of both the value of the inductance and the initial condition. So let's now look at an example. So we have this circuit here and we want to find the voltage across any of the components. They're all the same. We're going to call it this VT at time 0, from 0 going on. So the first thing I need to do is I need to draw my Laplace equivalent. So I am going to start with just redrawing my circuit here so you could see what we have. This was the circuit. 2 ohms, 0.2 farads, and 5 henries. And we had this with initial conditions of VC 0 is equal to 4 volts and IL 0 is equal to minus 1 amp. Now I'm going to redraw this in the Laplace domain. So I take my resistor and I redraw it in the Laplace form, which is the same as in the time domain form. I'm going to take my capacitor here and I'm going to redraw it in the Laplace form. And I'm going to use a current source. Since we're doing nodal analysis, it will make it a little bit easier. So this is my capacitor here. And now I'm going to draw my inductor in, and I'm also going to use a current source. And now I could fill in the information. So I know the value of this impedance should be 1 on SC. This is SL. The current source here is CV0 and the current source here is I0 on S. So now I could get to the business of writing my Kirchhoff's current law equation. So here I have Vs now because I'm in the S domain, and I want to write an equation for the node on top. So let's just assume this is ground. So I'm going to consider all the currents going out. So I have Vs on R, which is Vs on 2, plus, Vs over 1 on SC, plus, or in this case minus, CV0 plus Vs on SL, which is the current down here, plus I0 on S, and all of that is equal to 0. So I could substitute my values now, and I will get this should be 0.2, 0.2, L is 5, I0 is minus 1, and V0 is 4. Good. So what I need to do now, I have everything substituted. I'm just going to collect the terms in Vs. and form an equation for Vs. So you could go ahead and do that and work through it, and you should get something looking like this. Vs is equal to 8s plus 10 over 2, let me do this one first, 2s squared plus 5s plus 2. This should be your final answer in the Laplace domain for Vs. Now the question is, how do we bring it back to the time domain? So we're going to go through the same procedure we did before. We want to put this in forms which are familiar to us that we could find in the table. So I'm going to represent this as, I'm going to firstly factorize this, and I'll get 8s plus 10 over 2s plus 1 multiplied by s plus 2. And this is the same as a over 2s plus 1 plus b over s plus 2. And I can equate my coefficients just like we did before. You could work through this, and you should get a is equal to 4 and b is equal to 2. Now, that would give me 4 Vs is equal to 4 over 2s plus 1 plus 2 over s plus 2. Now I need to look in my tables and find these. Now in my tables I don't have anything with as plus 1, so I have to change it to the form s plus something. The coefficient of s has to be 1, like it is in this case here with the 2. So what I'm going to do is I'm going to take the 4 and the 2 out, and I'll get 4 over 2 into 1 over s plus a half plus 2 1 over s plus 2. And I could look up these forms directly. I know 1 over s plus a is e to the minus a. So this, when I bring it back to the time domain now, looking back at my tables, I should get 2 e to the minus half t plus 2 e to the minus 2t. And this is my final answer in the time domain. Now if I want to check and see if this is correct, I could look at my boundary conditions. So I could say at t is equal to 0, I should have this e to the 0 will be 1, e to the 0 will be 1, and I will have V0 is equal to 4 volts, which is the voltage across the capacitor, the initial voltage across the capacitor. So we know that is correct. And then at t is equal to infinity, I have e to the minus infinity is 0, e to the minus infinity is 0, so I'll get V infinity is equal to 0. And we know, of course, in steady state, the inductor will be a short circuit. Sorry, yes, the inductor will be a short circuit, so the voltage across it should be 0. So it looks like it's okay. Now, the next time we're going to look at, well, this time we looked at solving the circuits by directly converting them into the Laplace equivalents, and we looked at briefly at substituting, how we could find the initial and final values by substituting for the values of t. We could actually find those values, those initial and final values, directly in the S domain by using what we call the initial and final value theorems. So that is what we'll look at next time.